even with cryptographic hash functions and not saving plaintext passwords in the database, passwords do still get stolen. You hear about breaches, and maybe even your own password has been stolen in the past. So how is this happening? Are companies just not using good hash functions, or are they not using them at all? And certainly not. They are doing the right thing, but the attackers have figured out ways around these security measures. So it's now kind of an arms race between the attackers and the security researchers. So starting from this baseline point of storing hashed passwords, let's see what the attackers might do in order to see what the security people have done to mitigate it. So let's say even if an attacker does manage to steal the table, all they get is usernames and hashes. They don't actually have your password, so can they do anything useful with that hash? And yes, what they can do is create something called a rainbow table. A rainbow table is basically, the idea is the attacker knows a bunch of commonly used passwords, such as 1234556. That's actually one of the world's most common passwords. So they produce a list of, say, the 100 most common passwords, and then they just pre-compute the hash of those passwords, and that is called the rainbow table. So all they need to do is they need to know what hash function some web server used in order to turn a commonly used password into the hash for that password. And then after they steal the hashes out of your database, they can just compare the hashes out of this rainbow table. And if they find that hash, then they know your password was that. So how do they know what hash function your web server used? Well, if they've already stolen the database, it's safe to assume that they know what hash function you're using. Maybe they've stolen the source code as well. Maybe they just assume that you're using some standard library for the hash function, which is actually a safe assumption. So this whole attack is built around assuming that noob users will use common passwords, and unfortunately they do. So what can we do to mitigate this problem? Well, first, so let's look at how this works. This is the pre-computed rainbow table. So they just have that sitting somewhere. And then let's say they do manage to steal a table out of some database. That's the stolen table. All they have to do is go through these known hashes for common passwords and compare them to the hashes they stole. If they find a match, then they know that Joe's password is that. Okay, so to combat this, we use something called SALT. So in the breakfast-themed security terms, hash, and then we take a little bit of salt and add it to the hash. So what SALT is it's a random string that we, at account creation time, so when we're creating a new user, we just produce a random string. So here's that random string. It's not a hash, even though it looks like one. It's just a random hex string. And what we do with that is we add that string to the user's password. So let's say that the password the user selected is bad password. We're actually just going to put this random stuff in front of it before passing the string to the hash function. So we hash the salt plus the password you picked, and you get some hash value out. So what's important is that this hash value is different from what the hash value would be without salt. If we just hashed the password, we'd get a different hash value. Now we have a hash value that includes some random string in front of the password. So since the salt is random, the standard rainbow table is useless. So if we go back, if they have this rainbow table here, assuming no salt, then they're not none of these hashes are going to match up with the stolen database if the stolen database salted the passwords before hashing them. So the question, though, is, well, how does logging in now work? If the password was salted before hashing, then how do we compare whatever password they type in when they're trying to log in subsequently? So let's look at the whole process, starting from creating a new user, and then we'll look at how logging in works. So the user inputs their password. We pick a random string and put both of those as inputs into the hash function. And we get some hash value out, and we save that in the database, just as before. But now the question is, how do we, after the account is created, how do we log in? The user doesn't know anything about the salt, and you certainly don't have to type some salt in front of your password every time you log in. So how does it work? We can't just use like another random string. It has to be the same random string in order to get the same hash out. And you might think, well, maybe you just like use the same seed for the random generator or something like that. And you know, that is maybe one idea. But a more direct idea is we just also save the salt in the database. So the users table now has username, salt, and the hash of the salt plus the password. And the salt itself is not hashed. So even though these look like hashes, these are just random hex strings. But this is the raw salt that went into the password before hashing. So it's just saved right there in the table. So when we're logging in now, the user still only needs to know about their password. But the system knows about their username. They provide their username, so we go into the users table, we look up the salt for that user, and then add it to the password that they used when attempting to log in, produce a hash, see if that hash matches the stored hash. If it does, then they have successfully logged in. So now the question is, well, if we're storing the salt, isn't that still a vulnerability? If the attacker is able to steal this whole table, then they just get those salts. So can't they somehow use those to figure out passwords? And yes, they can, but it makes a lot more work for them to do, and here's why. So this is the user table. I'm not showing user names because they're not important, but let's say this user happened to pick a password of ABC. And remember, we're not actually storing that password, I'm just writing it over here. That is the password they picked. So the attacker has to take the stolen salt, combine it with, let's say they assume that ABC is a common password. They have to take one of the stolen salts, combine it with one of the common known passwords, run it through a hash function, and then compare it to the stolen hash. If it works, then they have figured out the password for this user, for the first user. Okay, but let's say also the second user has also picked a password of ABC. The fact that the attacker has discovered the first user's password, even though the second user has the same password, the attacker doesn't know that because the other user has a different random salt. So the attacker has to combine every common password with every stolen salt, run them through the hash function, and then compare them to every stolen hash. So the standard rainbow table without salt looked like this. So let's say we build a rainbow table of the 3 most common passwords. So here's that rainbow table. It just contains 3 rows without salt. With salt, it looks like this. We have to create a rainbow table containing the combination of those 3 most common passwords combined with every stolen salt. So here are the 3 most common passwords. We would compute the hash combined with one of the stolen salts. And we would have to do it all again for every other stolen salt. So essentially we are just multiplying the amount of work needed in order to produce this rainbow table. We're making the rainbow table necessarily much larger in order to be useful. And then the attacker has the stolen hashes, but they had to produce many, many more possible hashes, one for each common password multiplied by each salt they stole, and then they can start comparing them to the stolen hashes. And when they find one, they have only found that one user's password. They haven't found anyone else's password. So, although the attacker's job is harder, it is still possible. Computers are fast, and it's easy to program a computer to do a brute force rainbow table attack. So, how can we improve security further? Well, we're relying on the attacker, rather, is relying on a brute force algorithm. So the best thing we can do to defeat that is to slow down whatever it is that algorithm needs to do. We've already slowed it down by just making the job a lot bigger in terms of number of hashes they need to compute, but we can slow it down further by making it more expensive to compute the hash. So what a modern web server will do is use a computationally intensive hash function, and it should take about 1 second of compute time just to compute the hash. Normally you'd think of, computing a hash function should be very, very fast, like a microsecond or even just like a dozen nanoseconds or something. If your hash function goes from 1 microsecond to 1 full second, that's 1,000,000 times slower, and the attacker's job now just got 1,000,000 times harder. And this 1 second number is not some magical constant or anything. It's just, it should be something that the user is not really going to notice when logging in. It'll take 1 second roughly to log in, but to a computer, 1 second to compute one hash value is extremely expensive. And, it's enough to slow down the job of a brute force rainbow table to take like weeks or even months or years. But they do still do it. And it's important to note here that making the hash function computationally intensive, you can't just do something like insert a sleep into the hash function algorithm, because the attacker is just going to implement their own version of the hash function, and they'll just take the sleep out. So it has to be fundamentally computationally intensive, and there's no way to really make it faster. So what .NET does, or at least used to do, they're constantly updating and improving it, is something like this. They would salt your password and then run it through SHA-256 once to produce the initial value, and then just take that hashed value and run it back through SHA-256 10,000 more times. And so they feed the current result into the next iteration and feed that result into the next iteration. So the point is not to scramble the password more and more or hash it more and more. It's just you're doing it 10,000 times now, so it's going to take 10,000 times more computational power to compute this hash function. And you can't just skip iterations here and go straight to the end. You actually have to calculate every hash function on the way. There's no way to predict or reduce this computation down into just one operation. Even still, computers are powerful and they are plentiful, and we can throw a lot of computational power at any problem. And like I said, you do still hear about passwords getting stolen. It does happen. GPUs in particular are very good at computing hashes. Even if they take a second to compute, well, a GPU can compute 5,000 of them simultaneously. So another thing we can do, particularly to defeat GPU rainbow tables, is use hash functions that require a lot of memory footprint, where just the algorithm itself fundamentally needs lots of memory in order to compute. And GPUs, in order to have as many parallel computations as they do, each of the threads in a GPU needs to have a relatively small memory footprint. So a hash function that requires lots of memory will defeat GPU rainbow table attacks. Another thing we can do in continuing the breakfast-themed security is we can add pepper. I don't know who named these, but so pepper is similar to salt. It's just a random string that's added to the original password before hashing. But the idea behind pepper is you save it somewhere else. So instead of saving it in the users table or even anywhere in the same database, you save it maybe on a different database or even in an external file that's just on the web server somewhere. So now you have two different points of attack where if an attacker happens to steal the database, they have to also steal something else. So if they gain access to one, they haven't necessarily gained access to the other, and they can't really do anything unless they steal both. So salt and pepper are kind of the same idea. It's about defeating rainbow table attacks. Salt has to be unique per each user, and pepper doesn't really need to be. You can just pick one pepper for the full system, and the whole point of pepper is it's stored somewhere else, so it requires two breaches in order for there to be a vulnerability. But it's important with pepper that you don't reuse the same one for like a different system. Because then if they do manage to steal the pepper in one place, then they can go try it on one of your other servers. So hashing and salt and pepper all go into something called a key derivation function, or KDF. Basically, its job is to produce a key or hash given an inputted password. And its job is also to produce the salt and to produce the pepper and use the salt and pepper, look them up at the appropriate times when the user is trying to log in. The whole point of all of this, the KDF, is essentially to protect bad users from themselves. If you simply don't use a common password, you make the attacker's job much harder to begin with. But unfortunately, there are plenty of people that do use bad passwords. So, right, I already talked about some KDFs intentionally use a lot of memory, but this idea of making the hash function computationally intensive or using a lot of memory and salt and pepper, all of that is the job of this whole thing called the KDF. So the hash function itself is only part of the key derivation function. So it handles all of this, taking the input password, loading the salt out of the database, loading the pepper out of somewhere else, and determining if the user has successfully logged in. So in summary of this arms race, the biggest vulnerability is a bad password. So security developers are essentially trying to protect users from themselves. You can do a lot just by simply picking a password that nobody else is likely to pick and that is never going to show up in a rainbow table. If your password, or rather if your hash of your password does get stolen, it may take months for an attacker to actually do anything with it to actually produce the rainbow table. So if you hear that there's been a security breach in one of your accounts, the first thing you should do, obviously, is change your password. And even if you don't hear about it until like a few days later, chances are the attacker hasn't had enough time to even do anything with it. So if you it's still useful to go change your password. So I've been talking about how we do all of this stuff. This, though, is a databases class, not a security class, although security is important everywhere, so I'm talking about it. Fortunately, .NET has all of this stuff built in. We don't have to write our own key derivation function. We don't have to call a hash function. We just configure the .NET project to use something called identities, and it will automatically take care of this stuff for us. And the way it will actually work is user names and passwords will be stored in a separate database. That's why when you're working on project phase 2 right now, you're still not doing anything with passwords, and that's fine. The database you're producing right now will be the LMS database. We will create another database later that sits alongside your LMS, and that database's whole purpose is for storing usernames and hashes of passwords. But we will see that a little later on.